So before we continue with the next part, let me ask you, we have some time to think about which was the correct. So you want to create a commensurate potential from this Hamiltonian. By commensurate, I mean that the potential repeats in space at some point for a unit cell of type L. Which one of the two vectors would you take? The first one or the second one? So, any thoughts about it?
First one.
Yes.
Cosine is 2 pi.
Yes, absolutely. That's perfect. So, essentially, you can just take that's the right Q is the Q that is 2 pi times an integer after L size, because after L size you want to just repeat yourself, and of course the correct answer is the first one. The second one would only work if you take even numbers of alpha, so not odd numbers of alpha. All right, great, wonderful. So let's now continue. So now, instead of thinking about one-dimensional moire potentials that essentially were very useful, of course, to understand how the electron structure reconstruct, let us move on to two-dimensional moire potentials. And we are going to start with the simplest two-dimensional moire potentials. Start the moire potentials that appear in twisted transition metal dipole coordinates, but when you take different twisted transition metal dipole coordinates. So the basic idea is that if you take different indices, so you can think that the layer on the top is MOS2, the layer on the bottom is tungsten diselenide or disulfide, then these materials are semiconductors, right? And they have a certain gap, but this gap is different between this material. So what can actually happen is that at certain energies, you just have states from one material and not from the other one. So at this energy, for example, that crosses where the chemical potential crosses the blue band, but not the red one, all your moire states are going to live in one of the layers, and you can understand all your moire states as just coming from the electronic structure of the first layer, reconstructed by the electrostatic potential of the second layer. So the very, let's say, a nice feature of this twisted TMDCs, hetero bilayers that have different monolayers, is that depending on the doping that you take, you can have moire states that live just in one layer, if your chemical potential just crosses the blue band, or moire states that live in both layers. And of course, the simplest ones to understand is when they live just on a single layer, because we only need to understand the electronic structure of a monolayer transition metal dipole coordinate in the presence of a superpotential. So this would be analogous as putting a TMD on top of an insulator that could also not contribute to the electronic structure of the moire system. All right, so the way in which we essentially model this is we take a tie-bonding model for the valence or conduction band of the monolayer that has let's say, the band closest to the chemical potential, or whose band crosses the chemical potential, and then we integrate out the degrees of freedom of the other layer, and we just incorporate the effects of the other layer and of the moire of the other layer as a superlattice potential that is periodic in space. So this potential is very, very similar to the periodic potentials that we were discussing before. The only difference is now we are thinking about a two-dimensional. So this potential is now going to be periodic in the two directions in space. And of course, if you have a twisted TMD, since you have an underlying triangular lattice, your moire potential is going to have a triangular. And essentially, the moire lattice constant, or the moire length, essentially depends on two different parameters. It depends on what is the lattice mismatch between the two TMDs. So of course, TMDs have very, very similar lattice constants, but not exactly the same. So that is going to be one of the parameters, and the other parameter is going to be the angle between the two different TMDs. So essentially, with the angle, you can control the length scale of this moire potential. So now to start, let us think about how the electronic structure looks like if we don't include the moire potential, but only if we consider how the band folds as we take bigger and bigger unit cells. And let me emphasize that this is exactly the very same idea as in the one-dimensional moire without a power. So we start with the minimal unit cell in which you have just a single band, and we are just taking here first neighbor, like rounding model. Then if we take a 2x2 unit cell, then we get, of course, 4 bands. In a 3x3, we get 9. In a 4x4, we get 16, and so forth. And we take a unit cell that is large enough so that it is commensurate with our moire scale. So now, if you do the very same trick as before, so you compute your band structure in the big supercell that may have, let's say 20 by 20 atoms, and you expand that band structure in reciprocal space. So instead of just considering one single Bernoulli zone, you go through several Bernoulli zones so that your band structure repeats itself, and you pick the right band using this unfolding spherical wave procedure. You essentially see that in the case of a triangular lattice, you recover. In the case of the absence of moire potential, you recover your original triangular bands, right? So, or your moire bands are relatively complicated, but you see that you can always pick one that gives rise to the electronic structure of the minimal unit cell. And now, once you switch on your moire potential, the very same phenomenology as we observed in the 1D moire system happens again, namely that the moire potential creates anti-crossing between the different moire bands. So now, instead of having a fully connected band structure, you have gaps in the electronic spectra. And let me emphasize that these gaps that you see in the 2D moire have the very same nature as the gaps that we had in the 1D moire, and are essentially the gaps that we saw in the one-dimensional quasi-periodic potential. And then, of course, what you see is that when you project onto the electronic structure of the minimal unit cell, you again shatter your electronic structure in different mini-bands. So you get one mini-band at the very top, and then the electronic structure keeps being shattered all over momentum space. All right, so that is in terms of the band structure, right? But apart from the band structure in two-dimensional systems, it is very useful to think about the Fermi surface, which is essentially the points in momentum space in which you have weight at the chemical potential. So it's the collection of points in momentum space in which the energy is zero. You assume that your chemical potential is zero. So if you think about a triangular lattice where you have a certain, let's say, small hole doping, your Fermi surface is just a circle. So this essentially means that your electronic dispersion is E squared, as you have, for example, in the gamma point of the transition metal dipole, right? So you know that EMDs have several pockets in the Bernoulli zone. There are pockets in the K points. There are pockets in the gamma point. And many times in this twisted heterobilayer, the states that are important are the pockets in the gamma point. So this would be the situation that you would have. So a TMD with a small doping in which your pocket falls at the gamma point. Now, if you start making bigger and bigger supercells in the very same way that your electronic structure folded itself, and you got more band, your Fermi surface is also going to fold and appear several times in your reciprocal space. So essentially, if you start with this Fermi surface for the minimal unit cell, once you make a 2x2 unit cell, your Fermi surface looks a little bit more complicated. But let me emphasize that to go from this to this, the only thing that you have to do is to repeat this Fermi surface in space and displace it in space. So you can actually identify that this circle here is this circle here, and all these other circles there are just the repetition that you get from this supercell. And of course, if you start making bigger and bigger supercells, you see that your Fermi surface starts being more complicated, but all the time, the only thing that you are doing is you are taking your original Fermi surface and replicating it and folding it onto itself in reciprocal space. So here, although you no longer recognize a circle easily, you can actually see that, well, here is a circle that it fills almost the entire image. And then all this part here on the right belongs to another circle. All this part here belongs to another circle, and so forth.
How do we see the M in this picture, these two pictures? Can we somehow find 3 circles in the right picture?
So you're asking how to recognize.
Yeah, so if you would see the right-hand picture, would you be able to say that
if you had showed me this, then yes. But if I only see this picture, no.
Okay, so let's assume that you know the left.
Yeah.
How do you see it from the right? And it's 3, which I guess is 9.
Yeah. Yeah. Oh, yeah. That's a very good one. So you can think that as you go from, imagine that you go from gamma point to gamma point. Then if you do a 2x2 unit cell, you have to repeat the circle once. If you do a 4x3 unit cell, you have to repeat the circle 3 times. If you do 4x4, you have to repeat it 4 times. So you just have to read from this picture how many times you have repeated the Fermi surface, and how many times you copied the circle and displayed it. So that would be the way of reading your supercell from the Fermi surface of the supercell. But you need to see this one, because if you don't see this one, you actually that's a very nice point. Thanks. And one more thing that I forgot to mention, please don't hesitate asking any questions, and the more questions you ask, the better. And again, any question is welcome. All right, great. So now let us see what happens if we start taking this supercell and adding the moire. So you remember that we added the moire potential to in the band structure we essentially call miniband, right? So this very same phenomenology actually happens in the Fermi surface. And in the band structure, these minibands were characterized by having anti-crossing, right? And these anti-crossing were essentially related to the strength of the moire potential. So the very same phenomenology actually happens in the Fermi surface. So if you start with the Fermi surface of your folded band structure, namely that you start with the Fermi surface of a n times n supercell, you essentially see that your Fermi surface has, let's say, many crossings. Now, when you switch on the moire potential, you essentially start seeing anti-crossings in the Fermi surface. And these anti-crossings in the Fermi surface are just a reflection of the anti-crossing in the band structure. So the Fermi surface is just a different way of representing one cut of your band structure. So if you see anti-crossings in your band, you will have anti-crossing in the Fermi surface. And that is essentially what you see here. So, for example, something very nice to notice here is that a moire potential can actually change the topology of your Fermi surface. So you can go from a Fermi surface that in the folded case, let's say, crosses each other several times, to disconnected Fermi surfaces with just 2 pockets. So a moire potential can very easily change the number of Fermi surfaces, and it can even change what is the nature of your electronic excitation. So you can go from electron excitations to hole excitation. You can go from states that appear at the bottom of a band to states that appear at the top of a miniband, for example. This is just the very same phenomenology as this Fermi surface reconstruction. All right, great, wonderful. But this is essentially the Fermi surface in the supercell, right? So in the original unit cell, in the absence of a moire, we should see only one surface, right? We had a single Fermi surface. So a question that is worth asking is how the Fermi surface in the presence of the superlattice looks like when we project it onto the original unit cell. And of course, this is exactly the very same procedure as the unfolding procedure in the band structure. We just have to weight our Fermi surface, but this unfolding spectral function, and once we do it, we can essentially project it onto the original unit cell. So then let's go back to the original unit cell. So now this is just a zoom of your Fermi surface. So this Fermi surface here is a very same Fermi surface that I showed you just with a single side for unit cell. I just zoomed a little bit in the reciprocal space. So in the absence of a superlattice, you essentially see your the surface that was the basic Fermi surface. Now, if you take the Fermi surface in the presence of the moire that had the anti-crossings, and you fold it back to the original unit cell, what you actually see now is that your Fermi surface got shattered also. And once again, this is the very same phenomenology that you observe in the band. If your bands get, let's say, shattered once you project back to the original unit cell, also the Fermi surface is going to get shattered once you project back to the original unit cell. So in particular, as you will know, the Fermi surface of any electronic system needs to be a closed surface, right? You cannot have open lines, right, for a Fermi surface. But when you have a moire potential, if you project back to the original unit cell, you are actually going to see these open lines. So you are going to see Fermi surfaces that are not closed anymore. And let me emphasize that this is not just a, let's say, mathematical trick to revisualize the Fermi surface. This is exactly what you would see if you do under-resolved photoemission spectroscopy in a moire material. So when you do RFES, what you are actually measuring is the Fermi surface in the unfolded unit cell, right? So if you do RFES in a let's say triangular lattice with a without a moire potential, you are not going to see this folded Fermi surface. The Fermi surface that you are going to see is the unfolded one. So if you now take a twisted quantum heterostructure, for example, twisted dihalogenide, and you do RFES, you will see that your bands actually define a Fermi surface that is open, a Fermi surface that has open lines and that no longer corresponds to a closed system. And this is just a consequence of the moire potential. This is just a consequence of the moire potential scattering electrons at very specific momenta, and in particular of scattering electrons at the momenta defined by the moire period. All right, great. So this is everything that we needed to understand of the effect of moire potential to the Fermi surface of the material. Yeah.
In this case, then how do you define the Fermi energy? It's not one energy.
It is still one energy.
Okay. I mean, what's this X and Y?
Kx and ky. It's momentum
Okay.
space. Yeah, sorry, I should have put the axis here. This is momentum space. So all these Fermi surfaces are always in momentum space.
So this is still one energy or one single energy. The energy is not
Exactly. This is still one single energy. So this is one single energy, which is the chemical potential that you can take as zero. And this is that very same chemical potential in that very same zero.
Is there some physical consequence to that RFES from the fact that you
I mean, you would say, for example, in magnetic oscillation, magnetic field, right? So when you apply a magnetic field, essentially your states kind of travel with your Fermi surface, and you would directly see it there. So magnetic oscillation, okay, good point. Which is quite often one way in which you can actually see what is the twist angle. So if you want to see your twist angle in transport, you can do a magnetic measurement and see what are your signals of the oscillation. Are actually just a consequence.
oil superconductivity.
Huh?
If you have shatter Fermi.
In principle, for superconductivity, I mean, it's okay because you still have, let's say, primary degeneracy. You will still have states at opposite momenta. Let's say, I mean, it's for example the case of niobium diselenide. Actually, so in niobium diselenide, you have a charge density wave, right? So your
Anderson's theorem actually might.
it still works. This is a non-magnetic potential.
No, but I mean, you are shuffling the momentum, and now there are some momenta that you don't find.
But you always find the time reversal partner. You're actually right. So
Yeah,
the gamma point is in the middle, right? So you always find a time reversal partner.
Yeah, but the effect of these are actually might be here. These are kind of average these out. Or maybe it's actually uninteresting.
Yeah, no, but it's of course, let's say non-trivial will be the effect of this order here. Yeah, so let's say even if you have a shutter for the surface, this for superconductivity, it's not detrimental, and it's actually very good because you enhance the density of the state. We are going to go a little bit more in detail later on. So the most important thing is that this shattering of the Fermi surface is an observable consequence in the experiment. All right, great. So far we've been focusing on what is the effect of moire in the electronic structure and how our bond structures and Fermi surfaces change due to the moire, due to this reconstruction that somehow, let's say, shatters both our band and our Fermi surface. But maybe one of the most interesting effects of moire system is that we can actually get new states driven by these reconstructions. So every time that we have a moire potential, we have a new band structure, and we have a different electronic dispersion, and we have, of course, a different density of states. So let us focus again on this twisted EMDC. And before we continue, let me emphasize that this phenomenology that we are going to explore now is something that happens in any twisted van der Waals heterostructure. So this is not intrinsic of transition metal dichroconionized heterobilayers, but it's going to appear also in homobilayers. It's going to appear also in twisted graphene systems and in any twisted van der Waals heterostructure that has metallic states somehow. But we are going to focus on this one just because it is the easiest one for us. So again, we are going to take our moire superpotential, and we are going to focus on a chemical potential in which we only have states in one of the layers, and the other layer is just modulating the electrostatic potential and also for the strain of the layer with active electron. So now let us just look at how the band structure looks like of the system that has active electron as a function of the strength of the moire potential that we use. And first, if we look at zero moire potential, this consists just on the bands that folded in reciprocal space, but of course, without showing any anti-crossing whatsoever. So essentially, this is the very same electronic structure and the very same density of the state as the transition metal dichroconionized in the minimal. So, and now, as you start switching on the moire potential, so as you start increasing the effect of the underlying material, your electronic structure changes. And let me, of course, emphasize that in an experiment, you cannot adiabatically switch on the effect of a moire potential because it is not easy to move one material with respect to the other. But let's just take this as a let's say theoretical exercise for us. So experimentally, one can see the case in which you have one potential, the case in which you have the final potential, but you cannot see the intermediate steps. But let us look at the intermediate steps. So as you start switching on the potential, you see that you start increasing what is the splitting in between the mini bands. So at zero potential, you don't have any splitting, and then as you put a bigger and bigger coupling between the two layers, your splitting becomes bigger and bigger and bigger. And what is even more important for us is that as you switch on the coupling between these two layers, your bands get flatter and flatter and flatter. So you start with the electronic structure that has very few states at the top of the band, and you end up with an electronic structure that has a nearly flat band with many states at the chemical potential, or at the very least at this very same energy. So in other words, just by switching on a moire potential of a system that doesn't have electronic states and affecting a system that has electronic states, you allow for flat bands to appear. And this also has a consequence of the actual states. So you can now look at how the states look like in space as a function of the coupling. So if you take the, let's say, highest energy state of your system, so the state that is at the top of the valence band, and you look its evolution as a function of the coupling, what you actually see is that, of course, in the absence of coupling, the state essentially lives everywhere, right? So it is a delocalized state in the moire itself. But as your coupling becomes bigger and bigger and bigger, then your state starts localizing more and more and more in your moire itself. So this kind of phenomenology is actually very similar to what we saw at the beginning in this one-dimensional quasi-periodic potential, that as we switch on the strength of a modulation, our states go from being delocalized to being localized. Here, of course, the localization happens in the moire unit itself. So within the moire unit itself, you still have block waves that extend throughout the whole system, but the state itself within the moire unit itself gets localized as a function of the moire potential.
Sorry, this is something I always wondered, like the fact that they are flat in those points, is it because of the scale of the density?
Yeah, that's a very good point. So it depends on both the scale of the periodicity and the strength of the modulation.
Yes, the strength I understand.
Yeah.
This is fine. I was wondering, like, the fact that they have as flat is because of the scale. Because of the scale with respect to the normal lattice, like the ratio with respect to the normal lattice.
Yes.
Normal lattice.
Yes, absolutely. And actually, at least in these EMDs, the bigger your moire length, the easier for you to develop flat bands. And it's actually relatively easy to understand from this picture.
Yeah, it's this I wanted to think about it because go on, sorry.
Yeah,
Like
go on.
this momentum. How do you see it from here that it will rise as something flat?
Yeah, so let's go back to the 1D system that I think that there is even easier to understand. We had this. Okay, so this N, you can think about it as your moire, right? So now let's switch on a moire potential for length 2 and length 6. If you switch on a small moire potential, you're going to create an anti-crossing here, right? And then here we are going to create an anti-crossing there, right? And the more you pulse your bands, the higher your crossing appears in energy, right? So what this actually means is that the bigger your unit cell or the longer the moire, the smaller your coupling needs to be to create a full flat band, right? So in this case, if you wanted to create a flat band, you would need to add a coupling that has this full energy scale, right? So to pull all these states up there. But in this case, since this crossing is right there on the top, you can use a very, very small coupling to create a flat band. And of course, in twisted van der Waals materials, usually the interlayer coupling is weaker than the intralayer coupling. So you can think that the interlayer coupling is, let's say, around 10% the bandwidth that you see here. So of course, if you want to create flat bands in a realistic scenario, the bigger your moire length, the easier for you it is, because you can create flat bands with the smallest coupling.
But why only the uppermost, not the lowermost?
Yeah, the lowermost, of course. Yeah. So it's going to happen.
But what we saw there was that actually that flattening happens also some parts, not.
Oh, yeah, because I just zoomed in the top part, actually. Yeah, so let's say if you look, for example, at this band structure here, so of course the flattening of this top band is going to be stronger than the flattening of, let's say, this one, right? Just because this one has the crossing there. And what I was doing
Okay, it's now not symmetrical.
yeah.
So the simplest way to see it is like the longer the period is, the shorter the shift in the folding trending momentum.
Yes,
Which means the derivative, let's say, the change between one and the next will be very small, which means it will be flatter.
yes, exactly.
So
Yeah, exactly. That's the one. And this is, of course, something that is let's say, systematically used in experiments for twisted, in particular, EFDs. So usually let's say the smaller the angle between the two, let's say the strongly correlated, the more strongly correlated states we observe. Yeah.
Same band because we are actually isolating. We are creating some artificial zero-dimensional particles and which the energy are actually that form.
Yes, absolutely. And in this case, that is exactly what you see, right? So if you look at this picture, what you see is that you suddenly localize the states in very specific, let's say, quantum dots in your material. So you can also think that, especially this twisted transition metal dialphogenate and heterobilayers are a systematic way of creating a set of quantum dots connected to each other.
Different sizes and different separate contents.
Yes, so
Just 5 feet.
exactly. Yeah, you can control the size of your quantum dots and the distance between these quantum dots with just with the twisting. Let me emphasize that this kind of picture of quantum dots works very well for this twisted TMDC, but for twisted graphene, it is actually a little much more complicated. So in twisted graphene, one shouldn't think so much about isolated quantum dots and one should think a little bit more in terms of this flat band being pseudo-lambda levels of an artificial gauge field. In particular, in the case of graphene, the flat bands can be understood as lambda levels of a non-abelian gauge field that is actually driven by the modulation of the hopping in the unit cell. And this is very much related to this notion that I mentioned at the beginning, that every time that you have a quasi-periodic potential, you can map it to a quantum Hall state. So in the case of graphene, you can actually do an exact mapping between this hopping modulated in space for a Dirac equation and an artificial gauge field of a quantum Hall state in higher dimensions and also in 2 dimensions. So you can do both in both ways. All right, great, wonderful. So what we know now is that as we switch on a moire potential, so as we switch on the coupling between our 2D electron gas and the material that describes the potential, we essentially create both flat bands, and that these flat bands have states that are associated to electrons that are very heavily localized in the moire. So now let us think a little bit about this. So what we are doing is just by switching on a moire potential, we are drastically changing our electronic structure, right? So by switching on a moire potential, we are going from a situation in which electrons have a very large dispersion to a situation in which electrons nearly do not disperse. And of course, this has a very obvious consequence in terms of the density of the states of the group, right? So what this actually means is that you can essentially go from a density of states that has certain features to a density of states that has a very high divergence at the chemical potential. And in general, this twisting actually has this generic effect on the electronic structure. So for example, in the case of graphene, as you twist layers of graphene, you go from a situation in which you have a V-shaped density of the states, so a 0 density of states at the chemical potential, to a situation in which you have a divergence of the density of states at the chemical potential. And in the case of transition metal dipole coordinates, both hetero bilayers and homo bilayers, you go from a situation in which you have a metal, or let's say a semiconductor with a quantum density of states at the Fermi energy, to a system that again has flat bands and a divergent density of states at the chemical potential. And now this is maybe a very good time to recall the standard criteria that we were discussing in the session about magnetism. So in that session, what we actually saw is that if you have a certain density of states, essentially your electronic instability, and in particular your magnetic instability, is going to be the stronger the bigger your density of states is. So if you have a density of states that has V-shape, like in graphene, then it is going to be very hard for you to get a, let's say, correlated state. If you have, let's say, specific interaction. So from now on, let's keep the interactions constant and to a small value. Then if you have a metal, well, it may be still possible to get a correlated state, but if your interactions are weak, you are not going to fulfill this criteria. But if you have a flat band, it is very easy for you to fulfill the standard criteria. So even if you have very weak interaction in a flat band, you can very easily go to the correlated state just because you increase the density of states. So quite often in, let's say, twisted van der Waals materials, we say that we can, let's say, control the strength of electronic interactions with the twist angle. But the actual statement is that what we can control is the ratio between the interaction and the kinetic energy. So interactions themselves are constant, but we can control what is the density of the states of the system just by twisting one material with respect to the other. And if you think about that, any material, you always have some residual interactions. They may be very weak, they may be on the order of 20 MeV or maybe 5 MeV, but the bottom line is that if you make your bands flat enough, if you take a large enough twist angle, then you are going to fulfill this criteria and you are going to be able to go to the correlated state no matter what.
Can we put that then as the Fermi commented?
Sorry?
Something for like creating the flat band as the Fermi commented.
Yeah,
Fermi condition is a particular interaction driven.
yeah. So I think that it's slightly different. So let's say this effect that we are discussing is purely a single particle effect. So let's say here so far interactions did not matter at all. So this is a flat band that has just single particle origin. So from that point of view, I wouldn't say that this is interaction induced, but this is, let's say, just single particle flat band. All right, great. So now we have our flat bands, right? And maybe it is interesting to just compare how the electronic structure looks like without the moire, with the moire, and in particular to compare how the density of states looks like. So here on the left, you have the electronic structure I showed you before. I just flip it so that it is easier for you to see. And in particular, in the absence of the moire, or in the absence of the superlattice potential, you essentially see that your density of states is, let's say, finite at the chemical potential, and it's, let's say, completely finite, right? And it's, let's say, relatively small. So the density of states of a semiconductor of the bottom of the conduction band for a EMDC. But now when you switch on the moire, we saw that we got nearly flat bands. And now when you compute the density of states of this twisted EMDC with this nearly flat bands, what you actually see is that now your density of states is way, way higher, and actually even diverging at some point due to the Van-Hoff singularity of this mini band here. And this is the whole trick of this story. So as you go from a situation without moire to a situation with moire, your interactions stay the same all the time. Your interactions in principle don't change that much. You can think that it's some range Coulomb interaction, maybe some additional local Coulomb interaction, and so forth. But just by changing the value of the moire, you dramatically change the density of the states. And thanks to this, you are capable of coupling this sonic just with the twisted angle. And just as a very specific example of this, and this is of course something that you are going to do today in the exercise session, let me show you here how the correlated state in this twisted heterostructure looks like. So what we are going to do is we are going to take just a superlattice with that has, of course, hoppings and also the moire modulation, and add local interaction. So in the very same way as we did in the case of magnetism, and one can compute both what is the solution in the absence of the moire and the solution in the presence of a moire. So in the absence of a moire, you don't see any spin splitting, so you don't see any magnetization at all. And this is just because your critical view is way below the value that is capable of giving magnetism, so it's below the standard criteria. And this is of course the typical case that you have, let's say in a TMDC, a doped TMDC. So if you do a TMDC, the system usually remains a semiconductor, so it doesn't become magnetic, even though you have a certain carrier, just because the density of your system is not strong. But now when you go to the twisted system, then suddenly your bandwidth is much smaller, your density of states becomes much bigger, you fulfill the standard criteria, and then you see that a correlated state appears, and that a gap appears in the self-consistent solution, and this becomes a Moore insulator. So just with the twisted angle, you go from a doped semiconductor that has metallic behavior to a Moore insulator, just by the reduction of the bandwidth. And let me emphasize that this idea of getting correlated behavior from a superlattice is something that not only happens if you put two TMDCs, but it can happen in a single TMDC by itself. So many of the TMDCs, they actually have a charge density weight distortion. What this actually means is that you start originally with a triangular lattice of transition metal, and then this triangular lattice is metallic, and if it is metallic, it is prone to have charge density wave instabilities. The charge density wave essentially creates a new periodicity in your material. And this is, of course, something that happens in niobium diselenide, both in the H and P allotropes, and of course in tantalum sulfide and other allotropes. So in any transition metal like a coordinate that is metallic, you usually have a charge density wave distortion. Now, this charge density wave distortion creates by itself a superlattice potential. So the charge density wave is going to move some atoms of the unit cell, and now you may need to define a new unit cell that is periodic in space, and this new periodicity, together with the charge density wave, it's going to create mini-bands in your electronic structure. And in particular, for the case of tantalum sulfide, that is one of the ones that we discussed yesterday, in particular the 1T allotrope, and this also happens in 1T allotropes of other TMDCs such as iodine selenide, iodine sulfide, and so forth. What you actually get is that the charge density wave drives first the formation of a moire miniband, like the one that we saw here. And then once you have this moire miniband, the residual interactions that you get give rise to a local magnetic moment. So in particular, in the case of 1T tantalum sulfide, tantalum selenide, and even the sulfide, this correlated state that appears is actually a consequence of the moire electronic structure driven by the charge density wave. So moire effects can also appear in monolayers if you have an intrinsic modulation. And of course, all the magnetic properties of these allotropes are related with the correlated state in this moire potential created by the layer itself. The magnetic moment is a consequence of it, and the potential spin liquid behavior or frustrated behavior is also a consequence of it. All right, great. So now we already looked a little bit what is the nature of correlated states in twisted graphene, in twisted van der Waals materials. Let us now see how twisting can actually impact the topological properties of materials. And for that, let's start with something that we were discussing in the second session. So in the second session, we were thinking about superconductivity, and in particular, how to design superconductivity using unconventional superconductivity, using both conventional superconductivity, magnetism, spin-orbit coupling. And what we actually saw is that one of the ways of designing a topological superconductor was by picking a system with strong Brashka spin-orbit coupling, adding an exchange coupling that essentially opened the gap at the gamma point. And then when we put the chemical potential right here in the middle and added conventional superconductivity, the superconducting state was topological and gave rise to, let's say, chiral Majorana excitation. But of course, that is a trick that you can apply only in the top and bottom of bands, right? So only in the top and bottom of bands, you have, let's say, one state with one spin propagating in one direction and one spin propagating in the other direction. If you put your chemical potential elsewhere, you always have spin up and down propagating in both directions. So in terms of creating topological superconductivity through this scheme, you always need to have your chemical potential in some very specific parts of your band structure. So the parts that are parabolic and where your chemical potential just crosses once every spin channel. So if you think about this band structure, essentially, you will be able to create topological superconductivity when you put your chemical potential in the green region, or when you put the chemical potential in this green region on top, and then if you put it in the middle, you are going to get conventional superconductivity. But now, if you take, again, a super lattice, what you get is that your original electronic structure gets folded many times, and in particular, you develop minibands, right? And these minibands, they have their own top and bottom, right? So now you have, again, points in which you have a parabolic band right at the energies where, in the absence of the moire, you didn't have parabolic bands. So now what this actually means is that if you look at this band structure and you think about where you can put your chemical potential so that when adding superconductivity, you're going to get a topological state. Now there are many other places. So now you can, apart from the very bottom of your spectra and the very top of the spectra, you can also put your chemical potential at any top or bottom of any of the mini bands that you have. So just this effect of the moire of creating new mini bands just opens many new different channels for putting your chemical potential and allowing you to create topological superconductivity. So in particular, you can just compare the energy windows in which you will get topological superconductivity in the absence of the moire with the presence of the moire. So in other words, just by switching on moire potentials, you can create new topological superconductors in new energy windows that were not available before. So this is a very simple and minimal example of what is the impact of moire for creating topological superconductors. This, of course, also works for any other correlated, any other topological state. And for example, you can play this very same game if you create, let's say, artificial churn insulators. So, for example, you can create a churn insulator. So, a state that it's not superconducting but still has chiral edge state by combining a two-dimensional magnetic material with a two-dimensional metal, and getting at the same time right spin orbit coupling and exchange field. And if you do that, you can get quite often to situations in which, even though you have Rashba and exchange, your electronic structure has a gap. But now, if you switch on a moire, the moire actually opens a gap in your electronic structure. And in some of those situations, the gap that you actually get when you switch on the moire is directly topological. So the moire itself can drive topological states not only in artificial topological superconductor, but also in any other type of artificial topological state, like a churn insulator. And let me emphasize that apart from this, there's another case that we are going to address a little bit more in detail tomorrow, which is the case of churn insulators in twisted bilayer graphene. So in twisted bilayer graphene, we had that, or I mentioned before that the twist essentially creates an artificial gauge field that creates pseudo Landau levels. And Landau levels are, of course, very much related with churn insulators, and they are very much related with an anomalous hole conductivity. So the basic idea is that in twisted bilayer graphene, thanks to the Landau levels that appear just from the twist itself, you can get churn insulators in the absence of any spin orbit coupling, and just coming from the relation between, let's say, quasi-periodicity, Landau levels, and let's say high-dimensional quantum Hall states.
So, what is the definition of churn insulator?
Oh, yes. So it's so far. Let's think just about the system that has a gap, and in which electrons in one edge propagate in one direction, and electrons on the other edge propagate in the opposite direction. That is the definition that we are going to use so far. Tomorrow we are going to define them properly and their topological value. Yeah, yeah, great, thanks. All right, great. So I think that now it's a very good time to take a break. So I would suggest that we can take a 15-minute break until 5:11, and then during the break again get some air and think also about something else. But I would also like to ask you that if you have some time, you can think about which one of these band structure has more van Hall singularities, and these are just directly unfolded electronic structures in the minimal unit cell. So yeah, see you at 5.
How many of you know one house inverter?
Oh, yes, so that was a very good point. So, all right, let me phrase it in a different way. So, which ones of these electronic structures are going to have more density of states with divergences? Yeah. Great, thanks a lot. So, yeah, see you at 5:11.